I hope you're all having a good day. Thank you for joining me. I'm Mr. Ish. Let's look here at a very interesting situation. We have that y equals x minus 2 whole square, and then we also have y equals 4, a horizontal line. When you look at the first equation, you know it's a quadratic equation. If you were to graph it, you know you would look at something like this. It's horizontally translated, so the vertex is going to be 2, 0. If you wanted to determine a y-intercept, you can put 0 in place of x. You'll have y is equal to minus 2 whole square, which will be just a 4. Because it's a parabola, it will have a certain line of axis. It will have symmetry about that. You could also develop another point here, which would be 4, 4. If you put 4 over here in terms of x, 4 minus 2 is a 2. 2 squares are 4, so you have a 4, 4, you have a 0, 4, and then you have a 2, 0, and you have a parabola which is looking like that. Y equals 4, looking at only just from that interval 0 in terms of the x-axis, 0 to 4. It delimits everything to that region. If you were to just shade this in, you have that. It's like a closed shape. If you rotate this around the y-axis rotation, you're going to develop a good solid, a rotational solid. It would be solid, there wouldn't be any open spaces. It would be a solid which would look something like this. You would have that type of a development come in here and right here. But you know, all of this right here, everything internally, because it's a closed shape which is rotating, it should be all closed. I'm not drawing it closed because it becomes very messy. The only portion of this solid which would be open, it would be that area which would be represented by the mirror image. These two areas right here. When you're looking down over here, that area is open, but everything else above it in this rotational solid is all through and through closed. Everything is closed over here. And you can get a certain idea of what this shape looks like. How can you determine what the volume of this inside part is? How can you determine what the volume of the solid is other than that internal part which is open? Why don't we look at that? We can look at that, the internal volume of this open area, and then the volume of everything else which is all closed. We can do the larger volume first and the smaller volume second. If you were to look at each of these here in terms of a rectangle which is rotating around the y-axis, you know you can do cylindrical shells, and that's an ideal technique over here. You would have a radius here which would develop, and that would be x. Circumference would be 2 pi x. A height would be exactly the height of this rectangle from the top boundary line to the lower boundary line, yt, yb. What's your yt? It's your horizontal line 4. What's your yb? It's this function right here, x minus 2 whole square, which you can write as x square minus 4x plus 4, and that's exactly what it is. When you open this up, the 4's will cancel out. Your height of your Riemann rectangle would be minus x squared plus 4x. You will integrate everything here now, because you're looking at everything here with regards to the x-axis in terms of the intervals 0, 4. Volume with regards to x. 2 pi will get pushed out. You're looking here from 0 to 4, and then you know you have your radius component and your height component multiplying with each other. Minus x squared plus 4x dx. That right there is your equation form to determine the volume of that closed solid, not this inner portion underneath which is open. You have a 2 pi, you have a 0, 4 minus x cubed plus 4x squared dx. You can integrate this. This is a minus x to the 4 over 4 plus 4x cubed over 3. You're looking at it from a 4 and a 0 with a 2 pi pushed out. You can bring your calculator. You'll basically here have a 2 pi 4 to the power of 4 minus 256 divided by 4, which is a minus 64. Why don't we just write that? Minus 64 plus 4 to the power of 4, which is be a 256 over 3. That's exactly what you end up with. You can do a good fractional answer here. You'll have a 64 minus times 3 plus 256. You have a 2 pi times 64 over 3, which you know is going to be 128 pi over 3. That would represent the main volume of that solid. It would be 128 pi over 3. Everything which is closed other than this internal portion. Now we just have to look at that internal portion. We have that volume determined and it's set aside over here. Now let's look at the volume of this internal portion. We can erase all of this. That internal portion right over here is not hard by any means. You're looking at this. It would be like a reverse volume of this internal cone, which has a concave aspect to it. You can again do everything here with regards to what you see. Here's my parabola. You're looking at now Riemann rectangles on the inside part, and again you have x-axis dimension with regards to your radius. Radius here is x, circumference is 2 pi, and that x. Your height of your Riemann rectangles is from here to here. Your top boundary curve is now your parabola, your lower boundary curve is your x-axis. So your top boundary curve is exactly what you see, x minus 2 whole square. X square minus 4x plus 4 minus 0, which is your x-axis, which is meaningless. What's your interval going to be? You're looking at everything from right here to right here, because this internal cone shaped figure ends right over here at the vertex. So your interval is now 0, 2, but still along the x-axis dimension. Your integral becomes this. You have a 2 pi from 0 to 2, you have this, multiplying with your radius, x squared minus 4x plus 4 dx. And you can integrate this and it wouldn't be hard. You would have an x cubed minus 4x squared plus 4x dx. You can integrate this in the next step in terms of its antiderivative. You have x to the 4 over 4 minus 4x cubed over 3 plus 4x squared over 2, which is a 2x squared. From a 2 and a 0. We may not need a calculator. If you have a 2 over here, you have a 16 divided by 4. 16 divided by 4 is giving me a 4. When you look right here, you have a 2 times 4, you have a plus 8. Now let's come right here. 4 times 8 is a 32 over 3. From here, you're seeing a 12 over 1. You're going to have a 12 times 3 minus 32, a 4 over 3 times a 2 pi, which will tell you you have a 8 pi over 3. And that right there will be your volume of your internal portion of this rotational solid. This internal portion, which would be open right here, you can see this cone right over here. That right there, this internal part has a volume of 8 pi over 3. The solid which has rotated about this cone around the y-axis has a volume of 128 pi over 3. I know it is difficult to generate with the hand a good solid representation, but you can probably see how it was. We have two volumes here. The external volume of the entire solid, 128 pi over 3, not including this inner portion which was open, that has a volume of 8 pi over 3, and that right there was the examination in this video. Cylindrical shells was a technique utilized because it's so much easy when you're looking at something rotating on the y-axis. Think about cylindrical shell, because by means of the flip phenomenon you convert everything with regards to a dx. Everything regards to dx, even though you're looking at a vertical line of axis or a vertical line of rotation. Anyhow, thank you. Have a good day.